The accumulation of anions in the blood in excess of cations is associated with metabolic acidosis. There are various ways of measuring this and assessing this, including things like the anion gap, the strong ion gap, the base excess or the base deficit. And I'm going to visit all of these in this tutorial. I guarantee you'll learn something. The sour taste of acid. Metabolic acidosis. This is tutorial 4 in the acid-base series. In the previous tutorial, I discussed ions and the pKa. Ions carry electrical charge and they dissociate, and the tendency to dissociate is determined by the ion dissociation constant, or pKa. The further that is from the physiologic pH, the more dissociated the ion is, and we measure ionic activity in milliequivalents per liter, and this is known as valency. Electrical neutrality must hold across all body systems. Ions that are fully dissociated at all range physiologic pH are known as strong ions. They may be strong cations like sodium or strong anions such as chloride. The difference between the charge carried by strong cations and strong anions is the strong ion difference, and it is always positive. Electrical balance is provided by weak acids, bicarbonate, phosphorus, and albumin. This time, I'm going to discuss acute metabolic acidosis. I'm going to discuss the concept of buffers and compensation, the systems for interpreting acid-base balance, and how they interact with one another. I was walking through the ICU and was handed this blood gas. Now I'm going to call the patient Larry, but that's not his real name, and he's 42 years old, and this is the blood gas I was handed. And this is a random event that happened a couple of weeks ago. I know nothing about this particular patient. All I know is what's on this piece of paper that I've just blown up so that you can read it. And we'll go back through this multiple times during this tutorial. But briefly, the pH 7.19, acidotic. PCO2 is 32 millimeters of mercury, or 4.1 kilopascals, a bit low. Bicarbonate is 13.1, very low. The base excess is minus 16.5. The anion gap is 20. Sodium 126, potassium 3.1, chloride 96, lactate 7.2. And there were 3 pieces of information that I subsequently obtained that weren't on the blood gas. Ketones 0.6 millimoles per liter, albumin 21 grams per liter, and creatinine 293 millimoles per liter, or 3.3 milligrams per deciliter. Don't worry if you didn't catch this, we'll come back to it later on. In the mid-1960s, various consensus conferences, as I've previously mentioned, determined and defined what acid-base abnormalities were. Acid-base abnormalities that result primarily from changes in PaCO2 are known as respiratory acidosis and alkalosis. Acid-base anomalies that result from disorders of electrochemical equilibrium independent of carbon dioxide are known as metabolic acidosis and alkalosis. If I were to say to you, look at the bottom of Larry's blood gas, you will see that his bicarbonate is 11.9 millimoles, or milliequivalents per liter. Your first reaction is, well, Larry has a metabolic acidosis. And nearly all the time at that level, you will be correct. And if I asked you why the bicarbonate falls, you would likely say something like, because it's the most important extracellular buffer. Gold star, you are exactly right. The concept of buffering of acids in the body was introduced by Henderson of the famous Henderson Hasselbalch equation in 1908, and it's become a cornerstone in our understanding of acid-base chemistry. Subsequently, Henderson explained the loss of bicarbonate buffer as being caused directly by the accumulation of organic and mineral acids in the blood, and these are principally anions, in this particular case, chloride. Bizarrely, for 100 years, it seems to me that the majority of physicians have seen a dynamic change in bicarbonate concentration as being mechanistic in acid-base disturbances, rather than this metabolic byproduct of carbon dioxide being a safety net component in the maintenance of homeostasis. Within acid-base reactions, Bicarbonate is a passenger. It's there to mop up hydrogen ions. In and of itself, it cannot cause acid-base disturbances. Only the carbon dioxide moiety can do so. As I said in the previous tutorial, all positive charges must equal all negative charges. There aren't a lot of charged particles in the extracellular space. On the left-hand side of the screen, we have the positively charged particles in order of magnitude. Clearly the most important is sodium. On the right-hand side, we have the negative charges, of which there are more, and the most abundant is chloride. In the middle, we have the buffer systems: bicarbonate, albumin, phosphate, and hemoglobin. They're buffers because the pKa is close to the physiological pH. The organic products include lactate, ketones, and what I call metabolic junk products. Sometimes I think these are inappropriately called renal anions. When you're thinking about acid-base, I think it's really useful to consider that for every one of the positive charges, there is an equivalent negative charge, for example, a hydroxyl, and for every one of the negative charges, there is a positive charge, for example, hydrogen. So effectively, when chloride is inserted into extracellular fluid, it delivers a hydrogen ion and functions as an Arrhenius acid. Whether you agree with this or not, for most of the history of acid-base, including today, there are people who think that anions are acids, or at the very least represent the presence of acids. And if you are a user of the Anion Gap, you actually believe in this approach. Now, anions may be mineral, which are chloride, a strong ion, and weak acids, bicarbonate and phosphate. They function as buffers, or organic, the following of which are absolutely strong ions: lactate, beta-hydroxybutyrate, and metabolic junk products. Back in the 1950s, acid-base balance was sometimes called cation-anion or anion-cation balance because that's where all the business was. Remember, there are very few hydrogen ions out there. What's there are very strong anions and very strong cations, and when they get out of whack in their numbers, then you have acid-base abnormalities. To get a metabolic acidosis, there has to be either a gain in mineral anions such as chloride or phosphorus relative to sodium and potassium. So either hyperchloremia with normonatremia or normochloremia with hyponatremia, or a gain in organic anions such as lactate, ketones, or metabolic junk products. Key to understanding, though, of all of this is that bicarbonate is the major extracellular buffer. If the pH is low, for example, less than 7.3, and the bicarbonate is low, then the patient likely has a metabolic acidosis. A fall in the bicarbonate associated with increased hydrogen ion activity almost always means metabolic acidosis associated with a gain in measured or unmeasured anions, and this is really easy to quantify. The true beauty of bicarbonate is that, as a rule of thumb, and everything else being equal, for every 1 milliequivalent per liter increase in other anions acutely, there is a 1 milliequivalent per liter fall in the bicarbonate. And as a consequence of that, the traditional systems for detecting acid-base abnormalities have been used for 100 years. So when we are talking about systems, what we are principally talking about is how we assess metabolic acidosis. And that is to identify that an acidosis is actually present. In metabolic acidosis, due to respiratory compensation, that means looking beyond the pH to the bicarbonate and the base excess. The second thing to do is determine whether the patient is actually coping with the acidosis by looking at the PCO2 versus the bicarbonate, the respiratory compensation. Again, very traditional. The third system is to figure out what is actually causing the acidosis, and the bicarbonate-based systems fail miserably with this regard. So the following systems that I'm going to discuss are just tools, they are not mechanisms. The Boston approach, which is based on the work of Brackett, Schwartz, Relman, and Winters from the 1950s running into the 60s, is all about bicarbonate, pH, and CO2. They developed a series of rules based on observations of patients where they were able to figure out what should happen to the CO2 and the bicarbonate when the pH changes. And we've looked at some of these rules already in the previous tutorials. These were the rules we used looking at acute and chronic respiratory acidosis and acute respiratory alkalosis. And I found those rules to be particularly helpful. However, for metabolic acidosis, metabolic alkalosis, and chronic respiratory alkalosis, I don't really find these rules helpful. They're a little bit fiddly, there's a lot of counting, and they don't really serve to answer a lot of questions. Essentially, what the Boston group do for metabolic abnormalities is to look at factor 2, the respiratory compensation for metabolic acidosis, to see whether compensation is adequate or not. There is a mathematical relationship between the fall from normal in the bicarbonate and the fall from normal in the PaCO2. And if the CO2 fall is inadequate for the degree of fall in bicarbonate, there is a concomitant respiratory problem. The landmark work on this was performed by Winters in 1967, looking at the relationship between the PaCO2 and the bicarbonate or the base deficit. Winters' formula gives an expected value for the patient's PCO2. The patient's actual PCO2 is measured, and it's then compared to this. If the two values correspond, respiratory compensation is considered to be adequate. If the measured PCO2 is higher than the calculated value, there is also a primary respiratory acidosis. If the measured PCO2 is lower than the calculated value, there is a primary respiratory alkalosis. This is the first version of his calculation using the bicarbonate, and the calculation is 1.5 times the bicarbonate plus 8 plus 2. The second version of Winters' calculations used the base excess, or the 1 minus the base excess, the base deficit, something I'll talk about a little bit later on this tutorial. And in this, for every 1 millimole per liter increase in the base deficit or negative base excess, the PaCO2 falls by 1 millimeter of mercury or 0.13 kilopascals. I think this is so much easier to use than the other version. So if, for example, if the base deficit is minus 10, then the PCO2 should be 30. If the PCO2 is higher than that, for example, 33, 34, there is a concomitant respiratory problem. If the PCO2 is lower than this, for example, 25, there is a concomitant respiratory alkalosis. I think this is really helpful. If we go back and see our patient Larry, the amount of information that the Boston group will use here is very limited. So this is what they're going to use, and they're going to apply Winters' formula. And using the 1.3 times 12 plus 8 plus 2 approach, the patient's PaCO2 is higher than we would have expected. So this patient is not compensating properly. It doesn't tell us anything about the nature of the acidosis, just compensation. But that's important. Now let's move on and talk about the Copenhagen approach. A group of clinicians in Denmark had been following acid-base chemistry right back since the polio epidemic in the 1950s, and they originally developed the standard bicarbonate, but this evolved in the 1960s and early 70s into the base excess that was developed by Sigurd Andersen. And the idea of the base excess was to provide a measure of pure metabolic activity by removing the confusing respiratory component. This is one of the myriad of formulas about how base excess is derived. Keep in mind that the bicarbonate itself, a derived variable, is buried in there. So there's an awful lot of assumptions, not least the relative ratio of extravascular to intravascular fluid. But in this calculation, the base excess is the bicarbonate minus 24.8, that's the normal bicarbonate, multiplied by 16.2, which is a whole variety of different things. That's the non-bicarbonate buffers, hemoglobin, albumin, and phosphorus, multiplied by the pH minus 7.4. And what base deficit or base excess does is simplify the change in bicarbonate from baseline. So in this picture, we have a baseline pH of 7.4, and there is 10 milliequivalents per liter of excess negative charge, for example, a lactate of 10, and this immediately causes a fall in the bicarbonate by 10 milliequivalents per liter. The 10 now represents the base deficit, which is 1 minus the base excess. What that number means is that at 37 degrees Celsius with a PCO2 of 40 or 5.1 kilopascals, the 10 represents the number of milliequivalents of strong cation that is required to bring the pH back to 7.4. And frankly, this works really well as a scanning tool. When you look down your blood gas, if that's a negative number, there is likely a metabolic acidosis present. If there is a positive number, there is likely a metabolic alkalosis present. And the reason for this is that with the way this particular system works is that for acute respiratory acidosis or alkalosis, the change in the carbon dioxide tension of blood has no impact on the base deficit or the base excess. So that's 0. So if you see a minus base excess, there is an issue. If the base excess is 0 and the partial pressure of CO2 is high or low, you know you've got a respiratory problem. Now, there are other calculations for chronic respiratory acidosis and for metabolic alkalosis, but the most useful one in metabolic acidosis I've already mentioned from Winters is that the change in the PaCO2 from normal, which is 40 millimeters of mercury, is equivalent to the change in the base deficit. Irrespective of the pH, a base deficit equals metabolic acidosis and a base excess, that's the plus, is metabolic alkalosis. So if we look at Larry's picture and we get rid of all this other information, Larry has a base excess of minus 16.5. That indicates that he has a metabolic acidosis. That means it will take 16.5 milliequivalents of strong cation to bring his pH back to 7.4. Now, this is really useful for identifying that there is a metabolic acidosis present, but it doesn't clarify exactly what's causing that acidosis. So there are problems. Yes, the base excess quantifies non-respiratory components of an acid-base problem, but it doesn't clarify the mechanism. And to do that, we need to go back to electrical neutrality. Regardless of where you come from to this position, Boston or Copenhagen, you end up in the same place, the physiochemical problem of electrical neutrality. And ladies and gentlemen, I present you with the anion gap. There is a belief that the anion gap is something relatively new in acid-base, principally because most textbooks reference a 1977 article, but it goes way back to the foundations in the 1920s. I think it probably originates in 1936 with this paper by James Gamble, the Gambleogram, but he doesn't specifically mention the anion gap. You can see here, though, it looks like an anion gap. In 1948, we had Singer and Hastings talking about buffer-base anions versus cations. And in 1963, there is clear evidence that the term anion gap was widely in use long before the base excess was even mentioned. And indeed, there's a bunch of letters in the New England Journal in the 1960s that mention anion gap continuously as if everybody knew about this, but nobody seemed to publish an originating paper for the anion gap, and most of the credit goes to this particular paper in 1977 by Emmett and Narens, who talk about the anion gap. And I think it's actually worth reading a paragraph from this particular paper. The second effect of the addition of strong acid is the need for the retention of its anionic moiety to replace the negative charges lost with bicarbonate. When hydrochloric acid is added, each milliequivalent of bicarbonate lost is replaced with chloride. This is a representation of the electrochemical approach that's been around since the 1920s. If we look at our standard baseline, partial pressure of CO2 in the blood, arterial blood, 40 millimeters of mercury, cations, sodium, 140, potassium, 4, and about 2 milliequivalents per liter of magnesium and calcium. On the anion side, we have an albumin of 11. Now, the 11 is not the weight or molecular mass or anything else of albumin. This is the charge that's carried by albumin, so about 11 milliequivalents per liter. 24 of bicarbonate, 105 of chloride, that's the major extracellular anion, and then some other stuff, phosphate, citrate, fumates, just other junk. So if you write off the magnesium and the calcium, you can pretty much write off this stuff. And this is more or less what you're left with. And what you're left with, if you don't calculate out the albumin and the phosphorus, is a gap of about 15 milliequivalents per litre. It can be calculated out very easily, but back in the 1920s, 30s, 40s, 50s, etc., it wasn't something that you could just do on every patient every day because most people didn't actually measure the albumin. But it's there. So the cations minus the major anions, which are chloride and bicarbonate, there's a space missing, and that is a gap of about 15 milliequivalents per litre. If a patient receives, for example, 10 milliequivalents per litre of hydrochloric acid, then the chloride level goes up. All that additional hydrogen ion is soaked up by bicarbonate, so the bicarbonate goes down by equivalent amount. And because neither of these items affect the albumin and the phosphorus in any way, the anion gap stays exactly the same. Everything that happens in this system is measured. Now, many of our colleagues refer to this as a non-gap acidosis, but that is actually a ridiculous term. It should be called what it is, hyperchloremic acidosis. There is no other cause of a non-gap acidosis. It's binary, it's either there or it's not there. There's no mysterious other measured anion. For example, you cannot get a non-gap acidosis from too much bicarbonate, so call it hyperchloremic acidosis. In this situation, we're going to give the patient 10 milliequivalents per litre of lactic acid or lactate. What happens is that the bicarbonate falls by an equivalent amount. The chloride stays exactly the same, but if you don't measure the lactate, then the gap increases to 25 milliequivalents per litre. But of course, we do measure the lactate because it's on every single blood gas sample. So once you put in the lactate there, the gap is exactly where it began. So in the modern era, if you're going to measure or calculate the anion gap, please put the lactate in there because it's one of the major extracellular anions and it's measured in every blood gas. Looking at Larry, let's do an anion gap on him. So let's get rid of all the stuff that we don't need and look at the sodium, potassium, and the chloride. And the anion gap here is 126 plus 3.1 sodium plus potassium minus the chloride, 96 plus 13.1, which is the bicarbonate, and that gives us an anion gap. And that has been helpfully given to us by our machine. If you really think about it, the old anion gap from Emmett and Naren's era, and pretty much what everybody does, all it tells you is whether the patient is hyperchloremic or not. But I can tell you that if the chloride is more than 105 milliequivalents per litre, then the patient has a hyperchloremic acidosis. You don't need to do an anion gap. And this is the problem with the anion gap. It only distinguishes between hyperchloremic acidosis from other acidoses caused by unmeasured anions, some of which are now actually measured. It tells you absolutely nothing about alkalosis in its original form, and it relies on the presumption that the gap is normal, and that assumes that the albumin and phosphate are normal. But of course, I can tell you, virtually every patient who's admitted to ICU within 24 hours, their albumin goes from 45 or 50 grams per litre down to 25 or 20 grams per litre because of various different processes that stop the production of albumin. And of course, patients getting a lot of fluid, particularly for sepsis, where the albumin is diluted. As a consequence of this, James Figg sought out a correction for albumin, and he came up with this correction for albumin that can be applied to the anion gap, and it shrinks the size of the anion gap. And this is so easy. It's the normal albumin, which is 42 grams per litre, minus the measured albumin, which is what you've got on your chemistry panel, divided by 4. The normal charge ascribed to albumin, which is most of the anion gap, is 11 milliequivalents per litre. So if you follow this chart, which I think is a really useful rule of thumb, for every 4 grams per litre fall in the albumin, there is a 1 plus correction for the anion gap. The low albumin is relative alkalosis. you really need to apply this, or else your anion gap is artificially hiding a metabolic acidosis. When you're looking at the anion gap, for example, you have your alkalinizing charges and your acidifying charges, which is sodium plus the potassium minus the corrected albumin plus the chloride plus the bicarbonate. That gives you this corrected anion gap, which is really useful for this particular patient. In this particular patient, Larry, his corrected anion gap is 14.75, which is significantly lower than the 20 that we already mentioned. It's 5 milliequivalents per liter lower than the previous 20. But I will point out that there is a whole lot of other information being made available. For example, the lactate is already on the blood gas, and it's very easy to measure ketones with a little bedside ketone machine. Every diabetic in the world has these. A lot of guys who are doing triathlons, they have them as well. People who go on Atkins diet, for example, they have ketometers. So not being able to measure ketones is a bit of an excuse. And if you actually feed in all of the information that we have, which is the sodium plus the potassium, minus the corrected albumin, plus the chloride, plus the bicarbonate, plus the lactate, plus the ketones, I always measure 1.5 times the ketones are calculated, because all you get on the ketometer is beta hydroxybutyrate. There's also acetoacetate there, and I figure about 50% more than the beta hydroxybutyrate gives you a ballpark figure of where the ketones are. So 126 plus 3.1 minus 5.25 plus 96 plus 13.1 plus 7.2 plus 0.9 gives us a fully corrected anion gap of 6.65. And that is the number of unmeasured anions that are present in this patient's system. So what does that mean? That means that there is a surplus charge of 6.65 milliequivalents per liter of negative charge in the extracellular fluid. As metabolic acidosis is caused by mineral and organic acids, and we've already accounted for chloride, lactate, and ketones, all that is left is phosphate and metabolic junk products. Because the phosphate level, even if it's very high, will never get close to 5 or 6 milliequivalents per liter. What you're looking at is a lot of stuff that is accumulated because the patient is in acute kidney injury that's manifest by the high serum creatinine. In my view, the great value of doing any of these gaps is that we have now outruled all the other causes of metabolic acidosis other than renal acidosis. And this tells me that our patient, Larry, needs to be dialyzed. If you're just going to learn one thing from this tutorial, this is a simple diagnostic rule. For the vast majority of patients, metabolic acidosis is caused by hyperchloremia, hyperlactatemia, ketonemia, that is an increase in the beta hydroxybutyrate and acetoacetate levels of blood, and then metabolic junk products plus phosphate. This is known as renal acidosis. We don't measure metabolic junk products because we can't measure them. We will be at some stage in the future. But the bottom line is, once you outrule everything else, all you have left is metabolic junk products. If you have a base deficit of -5 or 10, follow this along. Is it caused by chloride? Is it caused by lactate? And we'll check the ketones. And if all of those do not point us in the direction of our acidosis, it is likely that it's caused by a renal problem. Now, there are other causes out there, which we'll cover in later tutorials, but for the vast majority of patients, that's it. An alternative to the anion gap has been proposed by followers of Peter Stewart, and I'm going to refer to this as the base deficit gap approach. In Stewart's approach to acid-base chemistry and the strong ion difference, we look at electrochemistry where all of the positive charges must equal all of the negative charges. And you're familiar with this because I just talked about it with the anion gap. But in Stewart's approach, you have to measure everything. So the sodium plus the potassium plus the calcium plus the magnesium minus the chloride plus the lactate plus the ketones. So they're all the strong anions and strong cations. And that gives us our strong ion difference of 14 milliequivalents per liter. That should be balanced by the weak acid pool, which is the charge carried on albumin, bicarbonate, and phosphorus. So the strong ion difference minus the weak acid pool equals 0. If there is a surplus between the two, there is a strong ion gap and there are unmeasured anions present. Just to illustrate this, we have our strong cations in green and our strong anions in red, and that is the apparent strong ion difference. It should be made up principally of bicarbonate, albumin, and phosphorus. That is the effective strong ion difference. If unmeasured anions are present, then there is a strong ion gap. I've never been entirely sure what the strong ion gap actually gives me beyond what I could get from recalculating the anion gap with all of the information that I already have. And frankly, I don't really see the point in having to calculate it out using the magnesium and calcium. And no research to date has really shown that the strong ion gap is hugely useful versus the anion gap. What I do think is useful, though, is developments that followers of Stewart have made. These are Fensel, Fig, Sheldon Magder, Story, and many others. And originally, Fensel suggested that one should calculate out the impact on acid-base balance of different alkalinizing and acidifying processes, for example, sodium, chloride, free water, albumin, etc. And then once all of these have been accounted for, all that is left are unmeasured anions. Now, there's a lot more to this, the whole process of water overhydration versus dehydration and their effect on electrolytes, that I'll talk much later in this course when we talk about Stewart, because they're not as important as they might appear on the surface. A really elegant, though, way of dealing with this was developed by Story, and that is the base deficit gap. This quantifies the changes in base deficit from sodium and chloride and free water and albumin. If you have a base deficit, then you can rule out the impact of hyponatremia, hyperchloremia, dilution, and hypoalbuminemia using this approach, and everything that's left can potentially be unmeasured anions. The calculation is really simple, and I do this all the time in the back of an envelope. It's the sodium minus the chloride minus 35, and that's the base deficit or excess for sodium, chloride, and free water. The second calculation is where you look at the alkalinizing effect of albumin, and this is 42 minus the albumin divided by 4. You're familiar with this number already, and that's the base deficit or excess for albumin. If you add the base deficit or excess for salt and water and albumin and put them together, that gives you a calculated base deficit or excess. And if you subtract the calculated base deficit or excess from the measured base deficit or excess, you get the base deficit gap. Let's go back to our patient Larry, and we're going to use all of the information we have here now. And we're going to look at the sodium minus the chloride minus 35. That's the base deficit for sodium, chloride, and water. It's 126 minus 96 minus 35. To point out here, this patient has a hyponatremic acidosis, a hypochloremic alkalosis, but the net effect on this is a negative base excess of minus 5, which represents principally the hyponatremic acidosis. 42 minus the albumin divided by 4 represents a base excess of plus 4 for albumin. So this patient has a metabolic alkalosis also. We've now identified 3 separate acid-base abnormalities. If we take the base deficit minus the base deficit calculated minus the lactate minus the ketones, we'll get our base deficit gap. So it's 16.5, that's the base deficit or the negative base excess, minus 1, which is minus 5, plus 4, so the base deficit for sodium, chloride, and water, minus the base excess for albumin. That just gives us 1 for all of those multiple different acid-base abnormalities. That's 15.5 in total, minus 7.2, which is the lactic acidosis, plus 1, which is the ketones. That gives us 9.3. And what that 9.3 represents is unmeasured anions or metabolic junk products. It's 9.3 milliequivalents per liter of negative charge. And this is the really true unknown base excess. At least theoretically, in metabolic acidosis, the base deficit gap should equal the corrected anion gap or the strong ion gap. Now, you don't have to be digging out your calculator to do these calculations. You don't have to get a piece of paper because smartphone apps these days do a lot of this stuff for you. And I fed all of Larry's information into the smartphone app that I use, and you can find this in the various different app stores on the internet. This app has calculated the anion gap at 21.2 and the corrected anion gap at 8.3. But then it goes a lot further because I've put in all of the numbers into it, and the gambelogram identifies unknown anions as being 9.9 milliequivalents per litre, which is pretty much the same as I got in the back of the envelope doing my various other calculations, particularly the base deficit gap. It also calculates out the apparent SID, the effective SID, and the strong ion gap, which worked out at 9.9 milliequivalents per litre. Pretty much the same as the base deficit gap. Very neatly, it also shows you all of the different acidifying and alkalinizing processes going on, so you can pick apart what's happening to your patient. Now, I find that people are far more impressed when I make a big list of these acid-base abnormalities on the back of the envelope, having done loads of calculations, than when I just show them the screen of my smartphone, where everyone just yawns and says, "Oh yeah, okay, so what are we supposed to do with the patient?" Let's review this tutorial. In this tutorial, we discussed electrical neutrality and then looked at the different causes of metabolic acidosis and how you can figure out what's going on by using different approaches that were developed over the last 80 or so years. We talked about the Boston School and its contribution, principally the work of Winters, who showed the changes in the PCO2 in relation to the amount of metabolic acid generated. And this essentially showed whether a patient was compensating effectively or not for their metabolic acidosis. This is very useful. We then talked about the Copenhagen school and its contribution, the base excess, or 1 minus the base excess, otherwise known as the base deficit, a very, very helpful screening tool on most blood gases that will help you identify immediately whether there is a metabolic acidosis or alkalosis present. The anion gap and its strength and weaknesses, and how you can adjust that anion gap for modern practice by adding in a correction for albumin and putting in the lactate and putting in the ketones and everything that's left are unmeasured anions. I then talked about the strong ion gap using the Stewart approach of the strong ion difference, and then a modification of this, the base deficit gap, which is a very easy back of the envelope calculation that I particularly find very helpful in my practice. And I've also discussed how smartphones are killing off all the fun in acid-base balance because they do all the work for you. Next time, I'm going to discuss lactic acidosis. I'm going to start with a discussion about lactate, this most misunderstood molecule, and its role in body in homeostasis. I'm then going to explain why lactic acidosis develops and how you should or should not treat lactic acidosis. Join me then, and I guarantee you'll learn something. So that was metabolic acidosis, an introduction and an explanation of the tools that we use to measure it. I'm going to move on to look at specific acidoses in the next couple of tutorials. The first one will be on lactic acidosis. If you're enjoying these tutorials, please subscribe at YouTube, leave me some comments and likes, and follow me at ccmtutorials.org.